In our additive manufacturing lecture today, we will talk about the printing techniques synonyms. So some of the techniques we discussed about before, they have a different naming. Some of them are new to us. So we are having the material jetting and the binder jetting, photopolymer vat, material extrusion, powder bed fusion. If we want to look into a layout for the 3D printing methods, so you have some 3D printing methods are depending on material extrusion, similar to the FDM. Then for the vat polymerization, we are having the SLA and DLP. For the powder bed fusion, which are polymers, we have the SLS. And for the material jetting, we have material jetting DOD. For the binder jetting, we are having the binder jetting method. For the powder bed fusion, which basically depending or producing metals, we are using the DMLS, SLM, and the EBM. Let's start with the material jetting. The use of the in material jetting, we are using ink jet printers and similar techniques to deposit droplets to be able to build materials that can be dispensed in a programmed way through a nozzle or orifice to build up our three-dimensional object or structure. So we can see here on the right the actual shape from additive manufacturing machine, and on the left we are having the design or the desired shape. So if you go to your CAD software and design a semisphere, then in additive manufacturing, after processing, it will look something like this. Of course, the accuracy and resolution of the part depending on the 3D printing technique that you're using, as we will learn going forward that each printing technique has its own resolution and ups and downs in terms of final product quality. Looking into a sketch or illustration for the material jetting process, we can see here we have a position belt. This belt is driving the nozzle on the X direction back and forth, and we have here the base moving in the axial direction forward and backward. Then we have here kind of fan or blower that will cool down the deposited material, and we have the print head here where you have the material being deposited through that nozzle. And we have as well an optical feedback sensor, or called as position sensor. This is basically deciding if the nozzle in the exact location that is needed or not to be able to deposit the material in space, so that you can create your final designed product. And in the base we can see there's a kind of minimal heating, not overheating that can melt the material, but a heating that keep the material flexible enough to be able to accept the coming material into the old material. Like when you deposit the material and you keep it cool down a little bit, if you put new hot material into it, then in this case they will not be homogeneous as one object. So this heating pad on the bed of the 3D printer, it will keep the base or the original material warm enough to accept and flexible to accept new material being added into it. So the droplets being deposited through the material jetting, they are made from photopolymers, which is like kind of wax-like material. As we said before, photopolymer is a polymer that is sensitive to light, similar to laser. Like when you focus the laser into this material, it will change in seconds into a solid, from a liquid to solid material. So basically this material is used to form the parts and to do some kind casting patterns as well. So these kind of processes are considered a 3D printing machines even though they're using inkjets, but they are using a nozzle that's been led through motors, through CAD program data, and able to create 3D three-dimensional structures or 3D objects as needed. Again, we are redefining here the photopolymers. We defined them in previous lectures. It's basically a useful material that transform from a liquid to a solid in the presence of light. So basically you can tune the photopolymers so that they can cross-link and harden in response to different wavelengths of light. So not necessarily a high energy lasers, but you can even create specially designed photopolymers that can solidify on a certain wavelengths of light, either less energy light or higher energy light. So basically the additive manufacturing processes, they can transform the visible or the ultraviolet wavelength ranges. So the material jetting extrusion uses multiple arrays of print heads so that they can print different materials. So if you want to change the material, usually you should change the print head, which we call it as a nozzle. So sometimes, in some cases, you need to print in two different materials. So you print the first part in the first material type with the related nozzle type, and then you continue you stop the machine, then you continue your printing with the new nozzle head and new material, so that you can create your desired object or design. And in some cases as well, you can use one material to build and the second material to support, as we will learn moving forward, that some 3D printing techniques, they need a kind of supporting material to keep the object solid in space. For a 3D geometry that include voids or overhanging structures, then in this case you need to create a support so that this support will be able to hold these overhanging surfaces, so that when the droplets of material, let's say wax, is coming into the desired point in space, when you're building a new layer of material above the older one, then you want to make sure this layer is well supported so that you will not have any kind of defects in your printing process, and this droplet should land on something so that you can keep them fixed in location until the point they can solidify and take the shape that you wanted. We can see here this is an exhaust flow design. So this is the main exhaust going into the engine body, but you can see here there is an extra material being added into it. For example, for this kind of pipe, these are all supporting materials that they will be eventually removed in the post-processing techniques, so that they can be smooth and to be able to achieve the final product that you need. So you can basically remove these supporting materials. So you, while printing, you firstly account for these supporting materials. So you print these supporting materials first, then you print your desired part that needs to be hanging in space, so that you will have the part solid. It will solidify with time in the shape you want it. If a secondary support material is used, then sometimes you use a water-soluble material, and so that the support can be removed through immersing the part in water and in water-based or alcohol-based liquids. So not always these supporting materials need to be removed by hand in the old way, but some of these supporting materials are being designed to be removed just by dipping that final part into a certain liquid, then it will melt away and you still have the other material in place in the shape you want it. As we mentioned before, the material jetting is able to print multi-materials and different gradient of material structure. Some of the applications for the multi-material parts, it can be a part with controlled hardness and flexibility, up to parts with different electrical properties. Then sometimes even in bioengineering applications, you need various regions to tissue engineered structures with different biological properties in different regions of the part. The binder jetting technique uses nozzles to print the material, same as the other techniques that we talked about. Instead of printing the build material, you basically print the material with glue. So the binder jetting prints the material with glue. We talked about it a little bit before. So this glue will hold the powder together in the desired programmed shape. So you're having here, this is the liquid binder, this is the glue, will go through the nozzle and it will be dipped on the powder bed in a programmed way and in a predefined path. Then of course, as we said before, this is the powder bed piston. It will go down as we are building layers. When we combine the liquid binder with on the certain points of the powder, these powder particles will combine to each other and be able to create the part you want or the layer you want. And eventually you will roll the powder roller over it to make sure it's even and clean from any kind of debris. So again, the binder jetting process, you deposit thin layer of powder, then your print head will deposit some glue patterns on the powder, and that will make the first layer. Then again, you will put a new layer of powder, then you follow it with the glue, then the process repeats itself, and the piston will go down with the thickness of the new layer generated, and the roller will push new powder to the surface, and process keep going until your part will be completed and ready to be cleaned and used. The benefits of binder jetting: firstly, it have a speed. It's not slow. It's a kindly, relatively fast process. Then you don't need any secondary support for the material, basically because your part is sitting inside a powder, so the powder is supporting the part from moving or from falling apart. So since the part is made of powder material, so small fraction of the volume will need to be deposited from the print head. So the rest of the part, as we mentioned, will be sitting inside that powder and well supported in place. Having the powder, the layer can be formed quickly using a raise of print head, which can be done basically in seconds. Then the powder, as we mentioned, that surrounds the part is supporting any sequent overhanging geometries. Then no secondary supporting materials need to be designed or applied during the process. The binder jetting technique is a full color 3D printing machine. It is able to create assemblies and sub-assemblies that are fully colored for different kind of applications and illustrations. So you basically set up the machine in a way to complete the color spectrum, and where it can be printed layer by layer. These parts later will be assembled, then produced in the intended colors for marketing purposes or for illustrations and academic and teaching purposes and all of that. Then eventually you can create parts that are colored for graphics, labels, and all visual features, where all of these features can be directly printed into the part as it is being produced. So we can see here, this is a part. This is a crankshaft with one piston assembly hanged into it. I can assume this is a stress analysis for the piston and the crankshaft during the compression cycle for the engine, and how does that affect all the crankshaft balance and the stress strain of that crankshaft. So in this case, it is very helpful to see a colorful illustration of your 3D printed parts for teaching or for engineering purposes. These are some examples of the binder jetting products. You can see here there is a compressor in here, which is a turbine. Then here you can see some kind of 3D designed top view of a village, same as I would assume it's one of these video games villages that are shown in the market. So you can basically, using this technique, you can 3D print anything for all kinds of purposes, either architecture or mechanical engineering, electrical engineering, analysis and design, and all of that. The photopolymer vat process, it's basically involving a selective curing for the pre-deposited photopolymers. It basically uses some type of light source. For the stereolithography, the first patented and commercialized additive manufacturing process, it worked by scanning a laser across the surface of a vat photopolymer. The platform just raise one layer of thickness below the surface of the liquid. Then the laser scans the first cross-sectional layer, attaching the layer to the platform, and so on. So you can see here an illustration of the photopolymer vat process. You have the laser up here, you have the cured object, you have the photoresin liquid in here, and the vat is in here. Then here you have your Y platform, which raises and lowers the product as needed. So the laser will go down and the photoresin will solidify, and the base platform will move up and down to build a new layer until you produce your final design or 3D object. Another illustration for the same process, you have the laser moving through lenses. XY scanning mirror will reflect the light on the point that is needed. You have here a sweeper to clean out any kind of debris or dirt on the printing surface. Then you have the layered parts that you can see the layers for already built over each other for the part. And you have the base of the platform that lowers each moment a layer finished. Then you have the liquid photopolymer here, and you have the vat container in here, and that's the laser beam. So the laser will form the object needed, and the photopolymer will solidify, the base will go down to be ready for the new layer to be formed. So the platform lowers within the vat one layer thickness. The material will flow over the top of the previously formed layer. So it forms the new layer over the previous layer using a blade or deposition device. And the process will keep repeating itself until it completes the final product needed. This kind of technique gives you best accuracies and surface finishes for any additive manufacturing process. So it's one of the best and additive manufacturing processes that can give you accurate and good surface finished 3D objects. new designs for the photopolymer vat technologies developing they are developed to use digital light processing projectors so that they can project an image of the layer on the surface of the vat. So in this way it will cross-link the photopolymer and convert the entire layer from a liquid to a solid simultaneously. The bad sides or the notes on the photopolymer process, it needs some support network to be able to build any kind of overhanging structures. Otherwise, these structures will be broke or having defects and deformations. The supports are usually made of the same material that the part is being printed with. These supports, they must be cut away and removed in the post processes so that the part is completed in its final shape. You can see here, so this part is printed through the photopolymer vat, and you can see it's in the design phase still, but during the design phase the supporting structure is already accounted for so that overhanging objects will not bend with gravity and weight. So in this case you'll keep it in place until it gets solid and be able to hold its shape. The next method is the material extrusion. This is one of the famous additive manufacturing techniques. It basically extrudes the material through a nozzle. Material extrusion machines, they basically work by forcing the material through a nozzle in a programmed way so that the final structure will be built. The built material is usually based on a polymer filament. This filament is exposed to heat, melts and get extruded through the heated nozzle, and kind of you can imagine it like a hot glue gun, but in a programmed and engineered way. Then we have as well the metal extrusion. For the metal extrusion, firstly you create the first layer of material by the nozzle on the base or on the platform. So the platform usually either moves down or the nozzle will move up so the new layer of material can be deposited. Material extrusion is usually considered simple, and the machines doing the material extrusion are considered simple and relatively cheap, and they are good for the office and home environment use. So a lot of kind of inexpensive extrusion machines are already in the market. Their price could be $700 up to $3,000 at the time of this presentation. They are sold each year to hobbyist companies, education institutions and hobbyists. So the low cost of additive manufacturing machines based on the extrusion are suiting everybody, either in terms of cost and the technology itself and the end product. It's somehow an acceptable product for initial validation and proofing.